This video will cover section 2.8 on curve sketching. The objectives of this video will be to discuss the first derivative info about the shape of a graph and the second derivative information about the shape of a graph. The function f is defined as increasing on an interval from a to b if x1 and x2 are between a and b, implies that f of x1 is less than f of x2. The function f is defined as decreasing on an interval from a to b if a is less than x1, is less than x2, is less than b, implies that f of x1 is greater than f of x2. Graphically, f is increasing or decreasing if, as we move from left to right along the graph of f, the height of the graph increases or decreases respectively. For a function f, which is differentiable on the interval from a to b, if f is increasing on the interval from a to b, then the first derivative is positive for all x in a to b. If f is decreasing on the interval from a to b, then f prime is negative for all x in the interval. And if f is constant on a to b, then the derivative equals 0 for all x in the interval. For a function f, which is differentiable on the interval I, if the first derivative is positive for all x, then f is increasing. If the first derivative is negative in the interval, then f is decreasing. And if the derivative equals 0, then f is constant on that interval. So you can determine from the function f if it's increasing or decreasing and decide what the derivative will look like. And if you know the derivative function, then you can infer what the original graph would look like. If f is concave up on an interval, then the second derivative will be positive in that interval. And if f is concave down on an interval, then the second derivative will be negative. The converse of both of these are also true. If you have the second derivative is positive, then the original function is concave up. And if the second derivative is negative, then the original function will be concave down. Pulling all of this together, we want to use information up from the first and second derivatives of g of x to graph the function. We'll find all local maximum and minimums of the function as well. So we'll identify intervals of increasing, decreasing, concavity, inflection points, maximums, and minimums of this function. So we'll start by taking the first derivative and finding critical numbers of g of x. The first derivative of the function is 6x squared minus 30x. We'll set this equal to 0 to find the critical numbers. The critical numbers of the function are 0 and 5. Now we'll take the second derivative of the function and we'll identify inflection points and then use the second derivative to identify if the function is got a local max or a local min. So an inflection point may occur at 5 halves. We'll have to test to see if it is an inflection point. Let's use the second derivatives test to determine if there's a local max or local min at the critical numbers. So we'll evaluate the second derivative at 0 and at 5. Since the second derivative evaluated at 0 is negative, then the function is concave down and we'll obtain a local maximum at the critical point. Next, we'll evaluate the second derivative at the other critical number, positive 5. Since the second derivative is positive, the original function is concave up, and there will be a local minimum at the critical point. We'll also need to test for intervals of increasing and decreasing, and we'll do this by using the first derivative test, by taking the critical numbers and plotting them on a number line, and then testing points from the intervals created from the critical numbers in the first derivative to tell us what the sign of the derivative will be. So I created a number line in the interval from negative infinity to 0. I've chosen the test point -1. When we evaluate the first derivative at -1, the output is positive, and we know from the beginning of this video that the function will be increasing. Next, we'll test the interval from 0 to 5 by plugging in +1 into the derivative. The output is negative, and we know for the first derivative, and we know that the function will be decreasing. This confirms that we have a local maximum at the value, the critical number is 0, which we determined using the second derivatives test. So this just justifies that for us. Finally, when we plug in 6 into the first derivative, the output is going to be positive. This tells us the original function will be increasing on that interval from 5 to infinity. This also supports that we have a local minimum at the critical number of 5, which we determined using the second derivatives test. Next, we'll do the same thing for the second derivative. So when we plug in 1 into the second derivative, the output is going to be negative. And so the original function is going to be concave down on the interval from negative infinity to 5 halves. When we plug in 3 into the second derivative, the output is going to be positive, and so the original function will be increasing from 5/2 to infinity, and then this tells us that 5/2 will have an inflection point. On the next slide, we will summarize all of this information and put it all together to graph the function. Okay, we can see that we have a local maximum at the point 0, 6. This 6 is determined by evaluating the original function at 0. A local minimum occurs at the point 5, negative 869. The 869 is found by evaluating g at 5. Our interval of increasing is negative infinity to 0, union with 5 to infinity. It's important to note that our intervals of increasing and decreasing will only be in terms of parentheses because you cannot be increasing or decreasing at an exact point, so you'll never be using brackets. This is the same for intervals of concavity. We have an interval of concave up from the point 5/2 to infinity and concave down from negative infinity to 5/2, and an inflection point at 5/2 negative 113 over 2. And the y value for the inflection point is found by evaluating g at the critical number of the second derivative 5/2. Let's put all of this together to graph. Okay, when we piece all of this together, we see that our function will be increasing from negative infinity to 0, where it will have a local maximum at 0, 6. It will then be decreasing from 0 to 5, where it will have a local minimum of negative 869, and it'll continue increasing from 5 to infinity. And then we can see the concavity matches up with our intervals as well. The next video will cover applied optimization.